Bismillah Rahman Rahim. Assalamu alaikum, dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access the course page on my personal website, arifpad.me. The other way is to download all the notebook files from the course GitHub repository, Arif PUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.2 of the sixth module, Overview of Machine Learning, for the course titled Tools and Techniques for Data Science. In our previous session, I tried to answer the three famous questions. What is machine learning? Why to do machine learning? And how to do machine learning? Well, at an abstract level, machine learning is the application of artificial intelligence that gives the machine the ability to learn without being explicitly programmed by understanding the relationships between the input features and the output label of the given data, and then formulating that relationship in a mathematical form. My dear students, this mathematical form is actually known as a machine learning model. In this module of machine learning, our main focus will be, of course, understanding the mathematics involved behind the machine learning algorithms. And then we will be using the Python famous scikit-learn library to create an instance of the machine learning model, train it, test it, cross-validate it, and then check out its accuracy using some evaluation metrics. If the results are not satisfactory, perform hyperparameter tuning and repeat. So my dear students, out of these 7 phases of machine learning lifecycle shown in this image on the right, which I discussed in the previous session as well, we will be spending much of our time in this sixth phase, and that is machine learning model creation, training, and evaluation. With this premise, let us move on to the agenda of today's session. My dear students, today I will start with a quick recap of some statistical measures like variance, covariance, and correlation. They are a must to know in order to understand regression. In today's session, we will not be using sklearn and will do all the math using NumPy for simple linear regression that involves a single input feature. In the next lecture, we will inshallah repeat the same for multiple linear regression that involves multiple input features, doing NumPy for all the stuff, and then we will move on to using scikit-learn in our next lecture, inshallah. Well, today, after having a intuitive understanding of how simple linear regression work, we will use the least squares as a cost function, and we'll see as how we can minimize this cost function to get the regression coefficients and derive the best fit line equation used for prediction in simple linear regression models. Well, after understanding the math behind simple linear regression, we will practically do all this on a toy dataset without taking the example of sklearn. And at the end, we will understand the evaluation metrics used in regression models. And we'll discuss the concept of homoscedasticity and heteroscedasticity using analysis of residual plots. We have a lot to do today, so let's start playing. Okay, so these are some of the libraries I will be using today. Okay, so first of all, let us have a quick recap of some important and related statistical terms. And if you are new to statistics, I strongly recommend that you should watch the descriptive and inferential statistics videos in module 4 of this course, whose links are mentioned over here. Well, statistics is the area of applied mathematics that deals with the data collection and organization, data analysis, data interpretation, and data representation. Descriptive statistics is used to describe, summarize, and present different data sets through numerical calculations and graphs. And on the contrary, this inferential statistics is used to make predictions and inferences for an entire population based on sample data from that population. Let us have a quick journey from variance to covariance and then from correlation to regression. So variance and standard deviation actually tells us how much a single variable varies with respect to its mean. It is calculated by taking the sum of the squared distances between the x values and the associated mean divided by the sample size. Over here, n is the total number of data points in a dataset. And of course, standard deviation can be calculated by taking the square root of variance. And this is the formula for standard deviation for a sample. Well, this bell-shaped graph shows a normally distributed data, which is the data in which the values are evenly distributed, both above and below the mean. This also describes the empirical rule for the 68, 95, 99.7 rule, specifying that around 68% of the data points lies within one standard deviation of the mean. Similarly, 95% and 99.7% of the data points, they lie within 2 and 3 standard deviation of the mean. I hope this makes sense. And let me quickly describe this with the help of our toy dataset over here. Well, consider these 10 random observations created as a numpy array in variable x. The code is simple. I'm using the formula as well as the numpy std method to calculate the standard deviation. And since I'm calculating the sample standard deviation, so over here I'm keeping the degree of freedom argument to 1. When you are using the formulas at your own, be watchful of the precedents and put on brackets for the correct answer. Let's execute this code. Note that the standard deviation is low, that is 2.7, and this is because this data is not spread much and is quite close to the mean. Note that the mean is 65.1 and the spread of the data is from roughly 60 to I think 69. So low standard deviation implies that most values in the dataset are close to the mean. Fine. Let's see this example now. Once again, we have 10 random observations which are quite spread in range, this time from 1 to maybe 100. And let me execute this code. and see the mean and standard deviation. This time the mean is 58.9 and the standard deviation is quite high, that is 40, showing more spread of the data from the mean. My dear students, if you are new to this, I recommend that you should do this math using a copy and a pencil for a crystal clear understanding. Okay, now we know that variance tells us how much a single quantity varies with respect to its mean. This covariance tells us the direction in which two quantities vary with each other. In literature, you may come across different formulas to calculate covariance. This first is the basic formula, and the other two can be, of course, derived from it. So this first formula says covariance is equal to the sum of how the x varies from the mean times how the y varies from the mean divided by the sample size minus 1. Well, the value of covariance can range from plus infinity to minus infinity. Let us calculate and understand covariance with the help of a toy dataset. Well, this is a dataset that a teacher has collected. The x variables, they contains the number of hours a student has studied on daily basis throughout the semester, 1, 2, 3, 4, 5, 6, 7. And the y variable contains the GPA achieved by the student. So there are 7 pairs of observations. For example, if a student has studied, let's say, 3 hours every day, he or she had secured a GPA of 2.5. Well, I have taken just hypothetical observations for the purpose of this example. They have nothing to do with the reality. Well, in this code cell, I have used all the above three formulas to calculate covariance. Once again, my dear students, I have written them in one line. While doing that, be watchful about the presence of different operations. Uh, I have also used the NumPy's COV method, which seems quite simple. I have displayed them, and finally I have used the scatter plot method of Seaborn as well to visually display our dataset. Let me execute the code of this cell. Great. Note that all the three formulas give the same value, and that is 2.16. The NumPy's covariance method has actually returned the covariance matrix, which is shown over here. 2 by 2 matrix in our case, and you see that the main diagonal contains the variance of x and the variance of y, while the other diagonal contains the covariance of xy, which is 2.16. My dear students, as I already said, that the value of covariance can range from plus infinity to minus infinity, and the value we have got is positive 2.167. Remember, the magnitude of covariance is not simple to interpret because it is not normalized, as it largely depends on the magnitude of the variables. Simply speaking, uh, we only consider or interpret the sign of the covariance, which is positive in this example. And the same is shown in this scatter plot as well. That is, as we increase the value of one variable, the value of the other variable also increases. Okay, let me execute the code for this example too. Same piece of code, but a bit of different dataset. See, the covariance this time is minus 2.8. And the negative relationship can also be observed from this scatter plot. Once again, uh, remember this magnitude, that is 2.8, has no significance. It just tells us the direction of relationship either being positive or negative between the two variables plotted on the horizontal and the vertical axis. And finally, this third example shows just four paired observations. Let me execute this. These four paired observations are in the four corners of the world, having zero or weak covariance. I hope covariance is clear to you. Let me move ahead and talk about correlation now. Well, unlike covariance, correlation actually tells us the direction as well as the magnitude of relationship between the two random variables. In statistical literature, you may come across different formulations of the correlation coefficients, normally represented by an R or this rho symbol. And this correlation coefficient is developed by Carl Pearson. And this can be obtained by, of course, normalizing the covariance, that is dividing the covariance of xy with the product of standard deviation of x and standard deviation of y. And this is shown over here in this equation 1. Well, by substituting the above discussed formula of covariance in this equation 1 and doing a little bit of simplification, you can derive these three formulas. And of course, all these three formulas will return the same value of correlation coefficient, which will always fall between minus 1 to plus 1. Let me once again describe this with the help of some examples. And this is the same data set, 7 pairs of observation between two random variables, study hours and GPA. In this code, I have used the first formula, that is this one, covariance of xy over sigma x sigma y. Let me execute the code of this cell. So the correlation coefficient comes out to be plus 0.98, which shows two things. First is that there exists a positive relationship between study hours and GPA, and moreover the magnitude is 0.98, and this magnitude tells us the strength of the relationship between the two random variables. So we can conclude that there exists strong positive relationship between study hour and GPA. Okay, so let me execute the code of this cell now. Well, here the Pearson correlation coefficient is minus 0.99. So we conclude that there exists a strong negative relationship between the two variables. So if you increase the value of one variable, the value of other variable decreases and vice versa. And here is a brief summary of how one can use the different positive and negative values of correlation coefficients as strong positive, moderate positive, very weak, moderate negative, and strong negative. I hope this makes sense. Okay. My dear students, I think now I have set the stage right to have a clear and deep understanding of regression. Simply speaking, a regression is a statistical technique that relates a dependent variable to one or more independent variables. It is used to predict or forecast the value of a dependent variable based on the known values of one or more independent variables. For example, if you want to find out the salary package of a graduating student given his or her GPA, then this is prediction. And similarly, if you want to find out the total sales of a company in the upcoming year, let's suppose 2023, based on the sales in last 15 years, then you are forecasting. Do go through with these self-explanatory points that compares correlation with regression to have a clear understanding of the two. And let me move on to the types of regression. Types of regression algorithms, which can be categorized based on the number of independent variables, shape of the regression line, and the type of the dependent variable. Well, here is the long list. Some important are mentioned over here. And in today's session, we are going to do a scuba diving to the most basic one, and that is simple linear regression. And before I proceed, let me clarify a confusion that exists in many students' mind, and that is this straight line and this curve shows a linear and non-linear relationship between dependent and independent variable. Well, my dear friends, this has nothing to do with linear and non-linear regression, as the linear models can also fit a curve to your data. So that's not the only defining characteristic between these two. So these two represent linear and non-linear relationship. Using linear regression, you can come up with such kind of curves as well. Okay, so simple linear regression. Uh, my dear students, in very simple words, a linear regression is a type of model where the relationship between a dependent variable and maybe one or more independent variables is assumed to be linear. The other assumptions are independence, normality, and homoscedasticity. And I will talk about homoscedasticity, inshallah, at the end of our today's session. There are two types of linear regression models: simple linear regression and multiple linear regression. And as the name implies, if there exists only one independent variable based on which you want to predict the value of the dependent variable, then it is a simple linear regression. And this table shows some examples like the price of a house is dependent on the covered area of the house, and similarly the the sales of a company is dependent on their advertising expenditures. Here the house price and sales are independent variables, while the covered area of the house and advertising expenditures are independent variables. Okay. Let me start by giving you an intuitive understanding of simple linear regression using these four graphs. Consider this top left scatter plot between one independent or input variable, which is the CGPA, plotted along the x-axis, and one dependent or output variable, which is the salary in thousand rupees, plotted along the y-axis. Well, these four data points x1, y1, x2, y2, and so on to x4, y4 shows the CGPA and salary package of four graduated students. XI is the CGPA and YI is the corresponding salary package. Now, since these four data points are collinear, so we can easily draw a line that passes through all the 4 points as shown in this top right line plot. This line is called the regression line, and we can use this to predict. For example, you tell me the new CGPA value that is not there in the existing data set, and I can predict the corresponding salary package that will be offered to that student. And this is shown over here in the dotted line. You give me a new input X and I predict, and this Y hat shows the prediction. We can solve this, of course, mathematically as well. For example, given these four linear equations, and after solving them, we get the line equation like y is equal to c plus mx, and over here it is shown as y is equal to beta naught plus beta 1x. We normally use these betas in machine learning, where this beta naught is the y-intercept and beta 1 is the slope. So to mathematically predict the salary package for an unknown x, that is a CGPA, we need to use this equation. Salary is equal to beta naught plus beta 1 times CGPA. This is the mathematical representation of a simple linear regression. Well, in machine learning, these beta naught and beta 1 are called the coefficient of regression that we will be computing for a given set of x's and y's values. This beta naught, which is the y-intercept, is the minimum value of the output variable y when all the input feature variables are 0. In this case, even when the CGPA is 0, the minimum salary is 40K. So this is just doesn't seems right, but I think you have got the understanding. I just want to tell you that this beta naught is the minimum constant value of the output variable. The second regression coefficient, this beta 1, is actually the weight that is multiplied with the CGPA. And I hope this makes sense. Now consider this bottom left scatter plot having 4 points which are not collinear. These are not exactly in the same line. The data seems to be sort of linear but not exactly linear. That is, we cannot draw a single line that can pass through all these 4 points. Now $100 question is, how can we draw a line that can pass as close as possible to all these 4 points? And such a line is called the best fit line. And to solve this problem, first we have to find the relationship between the x values and the y values. And for a two-dimensional data set, that is a single input feature and a single output label, this mathematical representation is of course the equation of the line, that is y is equal to beta naught plus beta 1x. So if we can somehow find the value of beta naught and beta 1 by understanding the relationship between these x's and y's, I can easily draw this best fit line by substituting the values of the x's and y's. So this is what simple linear regression is. I hope this makes sense. Let me just have a glass of water to wet my throat. Fine, let's move ahead. My dear students, I think now we have a fair idea of what is linear regression, rather what is simple linear regression and why to do it. Now the next $100 question is how to do linear regression. Once again, consider the same 4 data points or observations with x's containing CGPA and y's containing the corresponding salary package of a graduated student. In this right graph, let us assume that this blue line is the best fit line, which is passing as close to all the 4 green points. The green points are the actual observations, actual points, which are this best fit line is passing as close to these green points as possible. Now there are 2 colored points. The green dots are the actual points of observation, and the red dots are the corresponding predicted points. So for input, let's suppose x1, the actual output is y1, which is this 70 roughly, and the regression line is predicting the output as y1 hat. And this vertical distance between y and y hat is called the residual error. So for x1, the residual error is y1 minus y1 hat, this distance shown in red color. Similarly, for x2, we have the residual distance. We have residual distance for x3, and we have residual distance for x4 for all the 4 points. We can sum these residual errors for all our data set. So the equation for this blue predicted line is shown over here, and that is y hat is equal to beta naught plus beta 1 x plus some error which is a function of beta naught and beta 1. And remember, over here I have y hat. Y hat stands for the predicted value of y. My dear students, we actually want to find these two values, that is beta naught and beta 1, which are the regression coefficients, that is the y-intercept and the slope. So that when we plug these two values into this blue equation, this gives us the minimum value of this error function. And this error function can be calculated using these three formulas shown in red over here. Well, since this yi minus y hat, this value, this distance between the green point and the red point can be positive as well as negative depending whether the regression line is passing below or above the actual point. So this first formula is taking the absolute value. And the problem with this formula is that it is not differentiable. So in the second formula, we are just taking its square. So this function in the middle over here, where my mouse is hovering right now, is the sum of squares of all the residual errors. And since we use this to minimize this error function or loss function, therefore this technique is also called least square method. Although we will be using this middle formula, but due to this square, the unit of this error becomes different, and of course it is affected by outliers as well. So we can use this formula as well for the loss function, that is taking the square root of this. Okay. Well, my dear friends, the cost function that we have decided to use for best fit line is shown over here. That is the sum of the square of the difference between the actual value and the predicted value. So this is the difference. This is the loss function or the cost function, and we want to minimize this. I substitute the value of yi hat over here, and I can write the error function like this as well. And our goal to find those values of beta naught and beta 1 for which this error function will give us the minimum value. And my dear students, we can do this by differentiating this error function and later equating it to 0. And from our calculus background, we all know that differentiation is actually finding the rate of change of something with respect to something. And of course, it is very simple to differentiate a function with one variable. And over here we have in this error function two variables, that is beta naught and beta 1. Therefore, we have to use partial derivatives. That is, we differentiate our function with one variable at a time, keeping or considering the other variable as constant. So let us first differentiate this error function with respect to slope. And this is shown in graph 2. over here where my mouse is hovering, we have kept the y-intercept as 0 and have changed the slope. So these are some of the lines having different values of beta 1 or slope, and they are all passing through origin, that is the y-intercept is 0. And this graph on the bottom left shows the rate of change of the error function with respect to slope. We have different values of error function, and the minimum value of error function is over here where the slope is almost 0. Similarly, over here in graph 3, we have kept slope as 0 and have changed the y-intercept. So these are some of the resulting lines having 0 slope and a different y-intercept. And this model bottom middle graph, this shows the rate of change of the error function with respect to the y-intercept. So for different values of y-intercept, we have different values of the error function, and the minimum value of the error function is somewhere over here. Well, sorry, this is a typo. It should be E of beta naught. This was error for beta 1, keeping beta 0 as constant, and this is for beta 0. Okay. And finally, this fourth graph shows some of the lines where I have changed both beta naught and beta 1. That is, I have changed both the y-intercept and slope at the same time. So we can see that over here E is a function of beta naught and beta 1, which are like the knobs of a microwave oven. The way we need to adjust the knobs of a microwave oven to cook our favorite dish, the same way we need to adjust the values of these two variables beta naught and beta 1 together to find the best fit line, and to find the best fit line that passes as close to all these data points x's and y's as possible. And finally, over here in this 3D graph, bottom 3D graph on the right corner, I have tried to show the rate of change of the error function with respect to both beta naught and beta 1. Great. I hope the intuition is clear. Well, my dear students, now it is time to do a scuba diving behind the math that is involved to derive the regression coefficients beta naught and beta 1 for the best fit line using ordinary least square method that we have just discussed. I have just written it for you. Let me have a walk over it to give you a clear understanding. Okay, let's suppose that this is our best fit regression line, and that is y hat is equal to beta naught plus beta 1x, and if I know the values of beta naught and beta 1, you give me the value of x, and I can predict the output. That is, I can give you y hat. Suppose you give me some x's, x1, x2, x3, so on to xn, and I put them in these equations and get the predicted y's, y1 hat, y2 hat, y3 hat, and so on to yn hat. We want to minimize the sum of squares of residual errors, which is mentioned over here. That is yi minus y hat square, and we are taking the sum. Actually, this is our error function, and this is the function which we need to minimize. And we can open up this summation, this equation shown in red, and can simplify the equation by writing the square terms as a product of two terms by substituting the value of y hat as well, and we come up to this equation. And this equation over here, you can see that we can multiply the first term elements with each other and get the first term over here. So this first term, we have multiplied these two terms and I've got this. And I have multiplied these two terms and I've got this. And finally, I have multiplied these two terms and I've got this. So this is a bit simplified version, having the first term, plus the second term, plus so on to the nth term. And further, this can be simplified to this equation shown over here where my mouse is hovering. And this is simple multiplication. Please do this using a paper pencil. And finally, I have arranged these y1, y2, so on to yn, the square of all these terms together to this term, y1 square plus y2 square plus so on to yn square. And then I have collected these y1, y2 and so on to yn terms over here, and this x1, y1, x2, y2 so on to xn, yn term over here, and so on. So I've just gathered the terms together. And my difference, you know that a1 plus a2 so on to an divided by n, this is actually the a bar, that is the average of a. So if we multiply both sides by n, we can write a1 plus a2 plus so on to an as n times a bar. Therefore, this above expression can be written like this. You see the first term, instead of the sum of y1 squares, y2 squares so on to yn square, I have just written n y square bar. And in the same fashion, this long equation has been simplified to this. Great. So we have come up to this equation, this simplified error function equation, and we need to find the derivative of it. Well, this error function equation shown over here has two unknowns, beta naught and beta 1. Remember, these x and y's are not the unknowns. These are there in the data set. So we need to minimize this function with respect to beta naught and beta 1. And for this, we need to calculate the partial derivatives of this function with respect to beta naught and then with respect to beta 1, and then equate it to 0. Excuse me. Okay, so let us first calculate the partial derivative of e with respect to beta naught, which is written in equation 1. You note that all the terms which do not have beta naught are considered constants, and the derivative of the constant is 0. And the terms where we have a beta naught, for example, over here, and over here, these three terms have beta naught. We multiply the power of beta naught with the term and subtract 1 from the power. And finally, we get this equation 1. I hope this makes sense. And similarly, when we partially differentiate the error function with respect to beta 1, we get this equation 2. Great job done. Now, in order to find the minima, we equate both these equations 1 and 2 to 0. We equate this equation 1 to 0 to find the minima, and finally we land up to this equation 3, that is beta 1 x bar plus beta naught is equal to y bar. And this equation 4, I have simplified actually this equation 2. I have equated this equation 2 to 0, and I have arrived on to this equation 4. Fine, this is great. Well, my dear students, if you see this equation 3, the xy coordinates of a point on this equation are x bar, y bar, while in case of equation 4, the xy coordinates of a point are x bar, x square bar divided by x bar, and xy whole bar divided by x bar. So these are the 2 points. And now we have the 2 points, so we can easily calculate the slope using the formula of y2 minus y1 over x2 minus x1. And finally, here is the slope, and that is beta 1. I have simply use this formula to calculate the slope of these 2 points, and this is the equation of beta 1, equation 5. Note that by substituting this value of beta 1 in equation 3, we can find out beta naught as well. So these equation 5 and 6 are actually uh, the equations that we are going to use to compute the value of the regression coefficients, that is beta naught and beta 1. And we have all the values, that is all the x's and y's we have. We calculate beta 1, and once we have beta 1, we can substitute that value in this equation 6 and can get beta 0 as well. Great job done. Good. Okay. My dear friends, now let us do an example to apply what all we have learned so far. Consider these 7 data points, 7 x's and 7 y's, pair of data points. X is the number of hours a student studies daily, and y is the grade point, the GPA achieved. Let me first load this dataset from a CSV file into our data frame. So this is our data frame, study hours. This is the input column, input feature, and GPA is the output feature or label. Well, remember, study hours column is also called the independent variable, while this output column is also called the dependent variable. Okay, let me create a numpy array, capital X. This is just a convention that contains the input feature study hours, and another numpy array, lowercase y, that contains the output variable GPA. Remember, this uppercase X and lowercase y is just a convention that we use. And before we apply linear regression on this dataset, let us first check out if there exists a linear relationship between the study hours and GPA. And the easiest way to do this is plot your data using scatter plot. So let me plot it using the scatter plot method of Seaborn. So the relationship is linear and positive as well. Great. Okay, and from this scatter plot, you can simply observe that the 7 data points are not collinear. So there is no single line that can pass through all these points. And since this is a case of simple linear regression, so we can use the formulas to compute beta 1 and beta naught for the best fit line. And the formulas for beta 1 and beta naught for two variables, that is x and a y, that is 2D data, we have already computed. And this is the formula that we have computed. We have already derived this first formula. The other two are just a variation of it that you may come across in different books. So I've just written it so that you should not get confused. You can use any of these three. Well, I think the code is self-explanatory. I am just using numpy's method to calculate beta 1, which comes out to be 0.46. This is using the first formula, and this is using the second formula, and this is using the third formula. So using all the three formulas, we have got the same value of beta 1, that is the slope 0.46. Okay. Now we substitute the value of beta 1 in this equation and we get beta 0, which is 0.89. Great. Let's fit the line now. Before I use the line plot method of Seaborn to draw the line, I need to have the XY points. So I have used the NumPy's linspace method to create 100 evenly spaced numbers between 0 and 8. And to generate 100 y points, corresponding y points to these x points, I have used the equation, that is beta naught plus beta 1 into these x points of line. that is y is equal to beta naught plus beta 1 x. And finally, I have called the line plot method this time with three xy points, and let me execute it. So this is the best fit line. We got it. So study hours along the x-axis and GPA along the y-axis. Let's carry out the prediction now. Now we have the regression coefficient, so we can easily carry out the prediction. So the question is, a student has studied for 4.5 hours daily in the entire semester. Can you predict his or her GPA? And remember, this 4.5 is not there in the data set on which we have trained our model. Now it's simple like a piece of cake. Just substitute the values in the line equation, that is yi hat is equal to beta naught plus beta 1 xi. And let me execute the code of this cell. And it tells you that the CGPA is 2.989. So 4.5 hours, 2.989. And let me visualize this as well. And you see this is the predicted point shown in this red cross. So if a student studies for 4.5 hours daily, his or her predicted GPA is 2.9. Great. Well, once again, remember this beta naught is the y-intercept, which is beta naught is the y-intercept, which is what? Which is 0.89. Yes, this is 0.89 beta naught, and this line intersects this vertical line at 0.89. And similarly, beta 1 is the slope, having a value of 0.46 in this case. So it is positive. So it says that for every x, or for every study hour value of this input, the y value or the GPA value increases by 0.46 times the x value. And of course, we need to add the y-intercept to this. I think the interpretation of beta naught and beta 1 is crystal clear to you all, at least for our simple linear regression case. And let me move ahead and talk about the final part, and that is how to evaluate regression models. Well, my dear students, once you have trained your model, and in case of 2 dimensions have got the regression line actually, the natural question that will come to your mind is how to evaluate your model. And for this we carry out residual analysis. Well, as already said, a residual is the difference between the actual value and the predicted value of the dependent variable GPA or y. In this graph, the independent variable is the study hour, and the dependent variable is the GPA. And over here you can see 3 different colored points shown in green, red, and purple color. Well, these green color circles actually show the actual observations. These red colored circles are the corresponding points on the regression line, and that is y hat is equal to 0.46x plus 0.89. And these purple circles are the corresponding points on this purple line, which is the mean of the dependent variable, that is this y bar, which in this data set is a GPA of 2.75. Now, based on these 3 different points, there are 3 types of residuals that we normally use, whose formulas are shown over here: SSE, SSR, and SST. Well, let's talk about the SSE. We have already discussed this SSE, which is actually the sum of squares due to error, and is calculated by the sum of squared distances between the between the actual point yi and the predicted point yi hat. This I have shown over here using this red curly bracket, the distance between the actual point and the predicted point. The next is SSR, which stands for sum of squares due to regression, and is calculated by the sum of squared distances between the predicted point y hat and its mean, that is y bar. I have shown this distance with the orange color curly bracket. You can see that this is the predicted point y hat, and this purple is the mean, corresponding mean, and that this distance is known as a sum of squares due to regression. And the third one is SST, which stands for total sum of squares and is calculated by the sum of squared distances between the actual point yi and its mean y bar. I have shown this distance with this purple curly bracket shown over here. And remember, we have the differences for all the points, and we need to sum them up to finally come up to SST. And we have to sum up all the differences, the distances, to come up to SSR and so on. Okay. And finally over here we have R square. This R square is actually the coefficient of determination. It tells us how much variance in the dependent variable, in our case GPA, can be accounted for observing the variance in the independent variable, study hours in our case. Let me repeat, this is very important to understand. I know you can rewind, but I am repeating because this is important. This R2 score or R square score tells us how much variance in the dependent variable GPA can be accounted for by observing the variance in the independent variable study hours. And since it is the square of the correlation coefficient, that's why it is also called R square. In literature, you will come across different formulas to compute R square, R2 score. The most commonly used and the one used by scikit-learn as well is mentioned over here. That is 1 minus SSE over SST. That is 1 minus this sum of squares due to error divided by SST, that is the total sum of squares. Well, this value of R2 score normally range from 0 to 1. Let me describe this with the help of these three graphs. Well, my dear friends, in this left graph, you see a perfect best fit line. For a perfect best fit line, this SSE will be 0. That is y minus y hat will be 0. Both y and y hat are the same points. So SSE will be 0. When SSE will be 0, this term will become 0. So R square will become 1. This means 100% of variance in the dependent variable y is accounted for all these x values. Okay, in this middle graph, you see a reasonably good best fit line with an R2 score of 0.83 or 83%. And this means that 83% of variance in the dependent variable y is accounted for by the x values. And finally, this right graph, you see totally random points, and the regression line is a totally failure. The R2 score is 0% because this sum of square due to errors is equal to the total sum of squares, and this means none of the variance in the dependent variable y is accounted for by the x values. Uh, my dear friends, if your R2 score comes out to be negative, this means there is some error in your model. And finally, the limitation of R2 score is that it does not take into consideration the overfitting problem. Therefore, if there are multiple independent variables, you should use adjusted R2 score. And inshallah, we will discuss that in our next session of multiple linear regression. And here is a simple code where I have used these formulas to compute the four metrics for our study hours and GPA dataset. Let me execute the code. The mean absolute error, mean squared errors, and the root mean square error. These are the formulas: mean absolute error, mean squared error, and root mean squared error. These are just what we discussed above, just taking the mean. These are those error values which are quite small, good, and the R2 score is 0.96 for this particular simple linear regression model that we have trained on our dataset. So this R2 score of 0.965 means that 96.5% of variance in the GPA is accounted for by the study hours. Great. Okay, my dear friends, finally, here are the three residual plots of three different randomly selected datasets. I have just taken these images from the internet. Along the horizontal axis, we have the independent variable, and along the vertical axis, we have the residual, that is y minus y hat. In this leftmost scatter plot, you can see all the residuals are evenly distributed across the graph. So there exists constant variance, and a technical term that is used for this is homoscedasticity. In this middle scatter plot, you can see the residuals are much more spread out on the left than they are as compared on the right, making a kind of cone. So the error is large on the left, uh, and as compared to the error on the right. Uh, so there exists a non-constant variance, and a technical term used for this is heteroscedasticity. And finally, over here in the right scatter plot, you can see the residuals are in a curve shape. This shows that our data is non-linear, and a linear model may not be appropriate for this data, so you should change it. This is another type of heteroscedasticity. My dear friends, if the residual plots of your dataset shows heteroscedasticity, one option is to use some non-linear regression model, and of course we will discuss that in some of our future videos, inshallah. Okay, so my dear friends, at the very end, here is a task for you to do at your own time to check out your understanding of today's session of simple linear regression using ordinary least squares. Let me load the dataset in a pandas data frame on which you need to work. Well, there are simple two columns. Well, this input column, that is this uh, expenditures, and the output column is this sales. Well, my dear friends, remember the inputs in machine learning and during our series of sessions will go by different names like independent variable, this input expenditure. This can be named as independent variable or features or maybe predictors. While this output column sales, this go by different names like dependent variable or label or maybe simply response. Well, anyway, this dataset consists of sales in thousands of units of a product in 200 different markets. The expenditure column shows the advertising budget in thousands of dollars for the product in each of those markets. And what you need to do is you need to check out given this data set that if there is a relationship between advertising budget and sales, and if there is a relationship, how strong is that relationship, and is that relationship linear, and And finally, you need to check out how accurately you can predict the future sales for a new or different amount of advertisement budget for these products. I hope the problem is clear to you. I wish you all the very best for this task till we meet in our next session of Math Behind Multiple Linear Regression. My dear students, if you have liked this video, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.